After IPv4, the IPv6 was developed. Why? Because they tried to make it enough IPv4 and it was around 4 billion. And then they noticed that this might be exhausted because number one, some people might use duplicate addresses, so they made the private and the public. Number two, even still after the private and the public, it will get exhausted because of the evolution of technology and internet, etc. So they thought of in the 90s to develop a bigger IP that can host, that can cover more addresses, that can produce more addresses actually, and that was the IPv6, the Internet Protocol version 6, IPv6, instead of the decimal language that we have seen that cannot exceed 255 per octet, and the maximum was 2 to that power, and then we got the billions, etc. 2 to the power of 24, yes, we got that. 2 to the power of 32, I'm sorry, we got 42 billion, because 40 billion, 4 billions, I'm sorry, I'm so sorry, I'm exhausted, I'm so sorry. We had IPv4, and IPv4 was 32-bit in volume or length, and based on mathematics, 2 to the power of 32 gave us 4 billion and a little bit more addresses. Now, all of that was based on the decimal language and the 100 and the 32-bit length. Here comes the hexadecimal language instead of the decimal. So the decimal gave us 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then the hexadecimal says I will add hex for that, like A, B, C, D, E, and F. So now you have much more possibilities, but the length or the volume of that address will be, actually it will be 128 bit of length, and it's divided to 8 parts instead of 4 octets, 8 parts here. So let's see the difference in a minute. I believe 8 parts, this will lead that every part will be a 16-bit in volume or in length, yes. So 16 multiplied by 8 will cause us to 128. The hosts in total will be 2 to the power of 128, and that will lead to, I think I even read that number before, like it had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's a number that have 12 zeros to its right side, and that will be, not really, of course, I'm not that stupid. Like, no, it's not even 12. Oh, actually, it's 12 plays multiplied by 3, 36. Yes, that would be a number that has 36 zeros on its right, so that will make it not octillion, not septillion, no. But let me just tell you something nice. And there are a lot of options on Google actually. A 1 with 36 zero, yes. Not the sextillion, undecillion, yes, I'm sorry, the undecillion. And that is a definition plural, undecillion. The undecillion is a cardinal represented by the US 1 followed by 36 zeros. And we can see that this number here is 340 undecillion. Not just one single one decillion. No, it's 340 on decillion. This is how we can read this number, and that is too much. You can just like simply, if you have a really good calculator, you can take this number and you can divide that on the 4 billion of IPv4, so that you'll know how much IPv6 is bigger, or is a multiplications of the IPv4. An IPv6 then in that case would look like that. Let me show you an IPv6, how should it looks like. It will look like that form, like 2001, and then a colon. So no longer a dot representing an octet. It will definitely be a colon that separates each of the 8 parts. So like 2008, and then D, and then B, and then 80. It can be done in that way. And then perhaps a 0, 0, 0, 0. Why not? It's a hexadecimal language. And then perhaps a 1C, 1D, and then a colon, and then let's say 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, that would make them 1 2 3 4 5 6 7 parts, and let's assume in the end it was 0 0 0 1. So 8 parts representing the IPv6. All of these 8 parts, each part of them is separated by with the other by a colon. It must be a colon in that case, and eventually you can see that all of them were written using the hexadecimal language. There are no G, no H, no X, no W, nothing of that. It's based on the hexadecimal language. Now, just before I proceed, what I want to tell you is that the IPv6, because it's that long, that complicated, it might be very hard. It is very hard. Let's be honest, it has many years with that. It is very hard to keep writing IPv6 by yourself. So an IPv6, one address of IPv6 can be written in multiple ways. It can be simplified while writing that. You can express an IPv6 in multiple ways or in multiple patterns, actually. Like, let me describe the same example but in a simpler way, like 2001 colon DB80 colon, and let me show you DB80, yes, and like let's say 0 0 0 0 0 0 0 0 1 2 3 4 5 6th part, 7th part, and 8th part. If you think that this is an IPv6, that is correct. Let's check again. 4 parts and 8 parts. It looks nice. There is a second method of typing that, which is I can, instead of these 4 zeros, I can type one single zero. This will represent all of them as zeros. Why not? So that would be 2001 DB80, and right now I have just written 0 and a colon. So what will this computer or network device think? That this should be an IPv6, and in between the colons I always expect a 4 digits. Since I have so one single digits, then I will automatically fill it by using my brain and my calculator with 3 zeros, so that I will complete them to show up as 4. In that case, it's correct. Like if I wanted to represent the 0001, I can either like type all of them, or I can only type one. It can be done in that way, or let me do it in that way as well. 0010, that will be enough. So like this one was represented to look like one single zero. The other one I can do it the same way. The third one I can do it the same way. The fourth one I can do it the same way. This fifth and this final one, let me keep it, just stick with that. I can do it in that way. Another method will be 2001 a DB80 and a 0 a 0 a 0 a 0 a 0 and 1. Yes, because whenever there is something missing, the computer will automatically add multiple zeros on the left side of that digit, so that it will be look in total like 4 digits, the digit that you provided with the zeros that the computer has automatically filled in that way. So this is another method. There is a fourth method actually, or there is a different method called the double colon. We can use a double colon here to represent a group of hidden zeros. Like I can type 2001 and a DB80 and a 0, and yes, that would be a 0 here. I can do it in that way. Let's say just 0000. If you remember that, this one I have just typed it again, and I will do a double colon and a 0001. What I have just did right now is simply I have taken these 4 groups and I summarized them with double colon. So I hide those. I hide those. Yeah, I hide those, all of these zeros. 1 2 3 4 4 groups, 16 digits in between these 2 double colons. I can do that. Another way will be like even hiding more zeros, like 2001 and the DB80 and the double colon 1. What have I just done? I have just done something simple, and that was I have decided to make this double colons represent or hide these zeros, these consequence zeros, these zeros, and even these zeros. I can do it in that way. And of course, and definitely, when you see it in that way, it will look much better than this very long and complicated address. So we can represent an IPv6 in that way. Mostly it can have the subnet mask of /64, depends on the address type. There are subnet masks that varies from 64 up to /128, and perhaps you will need an IPv6 0 to hero course if you were like a senior engineer that might have a big migration project from IPv4 to IPv6. Then such simple video will not be enough for you at all. Then you will need to study that. Okay, so now I will go back to the slides and let's keep talking about the types of IPv6. There is something called the global unicast. It looks like 2000 double colon, like it's 2000 and zeros all the way, and sometimes it get changes like :1, :2, etc. And it has the subnet mask of 3. This is some special cases. It's public one. A unique local, like it starts with the F000 and it continues, so this is only the beginning, and it can be /7 or even smaller. A link local that starts from FE80 : and can be /10. It's a per interface assigned MAC address, I will tell you that. And any cast address, this can be assigned to multiple node to the nearest. This has nothing specific for now, but this is just the definition of what is an Unicast address. It's an address that can be assigned to multiple nodes worldwide, like multiple Google servers can have the same IPv6 address. Is that to duplicate over the internet? No, the route will be to the closest node. This is the use of the Unicast. Multicast looks like FF00 : with /8. This is a one source to multiple destination multicast that we will talk about in detail in the CCNP in core course. Okay, so there's a different thing that I wanted to tell you, which is called the link local addressing. The IPv6 link local addressing, which is a local address that's used only inside the device or inside its own domain. And just because the IPv6 is so hard to address and subnet and assign, then there is an automatic mechanism supported on Cisco routers, not switches or multi-layer switches, on the routers only. And these devices support the automatic creation of an IPv6 using the MAC address. So let's assume that the MAC address of a port, it's per port. So let's assume your MAC address of one port is like looking like, let's say, a 0000 : 001C : D201. Let's assume that this is your MAC address. It can be done in that way. Then the method of deriving a link local of that is called the EUI64, and there is a modified EUI64. So what I will do right now is that I will show you the EUI64. 1 minute. So that will be adding step number 1 is typing an FE80. It's very important. So this is step number 1. Step number 2, I need to add a double colon. This is step number 2. Step number 3, I need to take the first half of the MAC address and I need to clone it down. So I will type 0000 : 00. Step number 4 will be, I need to type, let me show you that, an F, that should be in purple because it looks like the FE80. The F, E. So where did these two came from? These you need to memorize in your brain. So FE80, you need to memorize that whenever you are writing a link local that you will never write seriously by your hand. The devices will create that automatically. And the double colon, you need to memorize that. And then the first half of the MAC address, and then an FE. Okay, and finally I will need the second half of the MAC address to be written down. So that would be 1C : D20 and 1. So I have just created for myself, for my port actually, a MAC address, and this is how a MAC address should look like. Now what I want to do will be in 1 minute. I need to show you something important, because this method, this very simple method of deriving a link local address from the MAC address is called the EUI64, but it's no longer being used because the method that is being used actually is called the modified EUI64. So I will just show you that simple modification to make a modified EUI64. I will need that in a minute. Yes. And I thought I lost that note because I forgot about the note. No problem, we can just type it right now. And the modified method will be to take the first byte of the MAC address and split that into two nibbles. And after I take the second nibble, let me show you that because I have written the note by myself. The modified EUI64 version says take the first byte of the MAC address. Where is my MAC? This one is my MAC. So I will take that. Okay, so anyone who's watching the video so far, this is the EUI64, and below I will type the modified EUI64, the modified version. Take the first byte. Well, the first byte is actually 00. Split that into two halves, and each half will be called the nibble. So this one is nibble number 1, and this second one is nibble number 2. So I needed two NIBBLES, two nibbles. Okay, so these are two nibbles that I have, and I will need to change the second. Okay, I will need to take that, and after I take that second nibble, I will look at the second nibble, no problem. 6 bytes, correct. This one is correct, yes, and I will need to take that. I did take that actually, and I will need to type 0 because it's 0. I need to type 0 in binary. Okay, so 0 in binary looks like 8 zeros actually. I did. And then what? And then I need to change the third bit to reverse it. 1, 2, 3. The third bit I need to reverse that. So it's either 0 or 1. I will make it a 1. So that will make the value of this binary as what? Well, it will be flipped as 0, 0, 1, 0, 0, 0, 0, 0. Okay. And in binary, this equals to 1, 2, 4, 8, 16, 32, 64, 128. Who's the one that is active? This one is the one that is active. It's 4. So it became as 4. Okay, so now that number is now no longer a 0. It should be a 4. And I will go up and I will delete this. And I will replace this with the 4 because this method has been derived in that way. And since it's a 4, then I will go down and a 0, 4. Okay, so a 4. I will need to change that to a 4. So it's as simple as that only. So we only needed to change that 0 with the 4 because this is what the third bit reversing caused us to. I know that this might looks like complicated, but to be serious, you will never do that manually. Seriously, you will never do that because the link local is supposed to be automatically generated by any Cisco router. You will not do that. You will design a real global and unique and private addresses, etc. with IPv6, but you will not design a link local at all. It will be automatically generated, and that's it. So this video is one single video for IPv6. Yes, it's not that much. We don't need to express that much, but perhaps in other courses and based on the agenda of other courses, we will go so deeply with IPv6. So I hope that at least it was clear for you so far. Thank you.